Section 5.6, we're looking at inequalities in two triangles, and we're looking at a type of proof called indirect proof. First thing we're looking at is, actually it's called the hinge theorem that we're leading up to, so we're going to do a little discovery here. Think of the triangles formed as a gate swings open. So this is like your actual gate, and you notice it's like this is the first stage, the gate is closed. Now we're opening the gate a little bit, opening the gate some more, and swinging the gate all the way open. And I want to look at the triangles that are formed, and first of all, what lengths are constant, and then what's the relationship between the angle of the open door and the length of the opening. So what lengths are constant? Well, the length of the gate is going to be the same always, so I could put a tick mark here, say, well, the gate's not changing length as it opens. Also, if you kind of think about the distance between the two gates here, this would be the same always, right? We're not going to be changing the distance between the two posts or between the opening in those two sides of the gate. So that's the same always. And now my question, what's the relationship between the angle of the open door and the length of the opening? Now, angle of the open door, I'm looking at this angle here as related to the length of the opening. This would be the distance of the opening here, opening, and distance of the opening in this case. Well, very small angle, very small opening. Larger angle, larger opening. Obtuse angle, huge angle, and very large opening as well. And you can see, because these two lengths were the same, the actual gate itself and the distance that the posts were apart from that gate, these are always the same, but as the angle increases, so too does the distance between the opening. This is what hinge theorem is dealing with. And we call it hinge theorem because of the idea that we can think of that open door situation. Hinge theorem says, if two sides of two triangles are congruent, like we had with the gate and its opening, and the included angle of the first triangle is larger than the second, then the third side of the first triangle is larger or longer than the second. So let's look at the picture here. If two sides of two triangles are congruent, yes, two sides of these two triangles are congruent. We had one tick mark and two tick marks, one tick mark and two tick marks here. And if the included angle, remember included angle is angle between the two sides you're looking at. So the included angle of the first triangle is larger than the second. Yeah, the included angle here was 98, which is larger than the included angle here of 46 degrees. Then what can I say? I can say the third side of this first triangle, side XW, is longer than the second, is longer than this third side of this triangle, or ST. So if this picture is true, then I can say that side XW would have to be longer than or greater than the length of side TS in that other triangle. Why? Because since these two sides were the same length and the angle here is greater, we know the side opposite would be greater than the side here because we had a smaller angle. We know that a larger angle means a larger side opposite from it. Smaller angle means smaller side opposite from it. And with these two congruent sides, that has to be the case with the third sides. And then we have converse of the hinge theorem, which just reverses the way it's written. Here we have if two sides of two triangles are congruent. So again, that condition has to be met. We have these two sides congruent. But in this case, we have the third side of this first triangle is longer than the third side here. We have the side of 12 is the other side, the non-congruent side, and a side of 9, which is the non-congruent side here. Then I would reference the angles and look at the included angle of the first triangle, this angle B, which is between the two congruent sides, opposite from that side of 12, would have to be a larger angle than angle E, the angle opposite from that shorter side in comparison here. So my conclusion, because I had two congruent sides, and I had this side, the third side was greater than the third side here, then the angle B would have to be a larger angle than angle E, seeing that that side opposite was greater. So hinge theorem and converse of the hinge theorem, let's use that in an example here. How would angle ACB compare to angle ACD? Angle ACB is right here. How does that compare to angle ACD? ACD, which is right here. Let's see if we can use hinge theorem. I notice I have congruent sides marked here. A side of 16, a side of 15. Now to use hinge theorem, you need two congruent sides. Well, this side here, AC, is shared between those two triangles, so they do have two congruent sides, a 1 tick mark, 2 tick mark. So if this last side, the third side here, is greater than this side here, then because those sides are congruent, doesn't that mean this angle, this opening, had to be larger than this one here? Because the side opposite was greater. So I can say that this angle ACB would have to be greater than, I should be saying, measure of angle ACD. Because of the fact that the side opposite was greater. Now this is converse of the hinge theorem. Because of the fact that I had the two congruent sides and I had the third side being larger than the third side here, I know the angles opposite have the same relationship as the lengths of the sides. Alright, an example here where I get to draw a picture. So I'll read the situation first. We have two runners start together but in opposite directions. They both go 1.5 miles, turn, and go 2.5 miles in another direction. So they go the same distance to start, they turn, and they go the same distance in the second part. The first runner goes north and turns 100 degrees east. The second runner goes south and turns 130 degrees west. Both runners return to the beginning. Who went further? Well, I know they went the same distance at the beginning and then on their turn, so I guess it's a question of who went further on that last part because of the degree of turn. Let's check it out here. They start together but opposite directions. So the first guy, we'll do in blue. First runner goes north and turns 100 degrees east. Remember how they go 1.5 miles first, so north 1.5 miles, and we'll do a compass just like this: north, south, east, and west. And I always remember the compass by it because it says "we" right there. So if he goes north 1.5, we'll say that this is 1.5 miles. That distance is 1.5. Then he turns 100 degrees east. The thing about this turn is like it's a turn instead of going straight, right? Because he was running straight ahead. So instead of continuing to go straight, he turns 100 degrees to the east. Instead of going straight north, he turns 100 degrees east, which 100 degrees would be slightly obtuse here, so that this is 100 degrees. He turns that towards the east, so towards the right. And then that second part was 2.4 miles. Probably a little longer, right about there. Alright, that's the first guy. And then he would go back home by taking this path. That's what I'm interested in. The second runner, he goes south and turns 130 degrees west. Okay, so he goes south to start. Remember, the same distance as the first guy. I think I drew that a little bit further than I meant to there. And they both went 1.5 miles at the beginning. Then, instead of continuing in a straight line southward, he turns 130 degrees west. So instead of continuing to go south, he turns toward the west, which would be turning left 130 degrees. So that's obtuse, even more obtuse than the last guy. 130 degrees. And he goes his 2.4 miles. He did a little long again. And then the question is, how far does he have to go back? Now my picture is not the best, and I'm sorry about that, so I'm really going to have to rely on what I know from the pictures. Well, first of all, these sides are congruent. They both went 1.5 miles in the first direction. These sides are congruent. They both went 2.4 miles in the second direction. My question is about these last distances getting home, because I need to know who went further overall. Notice that the angle I was given is not actually the angle in the triangle, and I need the angle in the triangle. But these are a linear pair, so they should add to 180, making this 80 degrees. And with 130 and 50 degrees, those would add up to 180. So now the question is, which of these sides is longer? Well, we have two congruent sides, an angle of 80 and an angle of 50 in between. With an angle of 80 degrees, this side is longer than this side because the angle is smaller, so this would have to be shorter. Therefore, If this distance is longer because the angle between two congruent sides was greater, I know that the first runner went further. His last distance, he had to cover more ground. Okay, so I had to find the angle actually in the triangle. This is using hinge theorem. I have two congruent sides in both of these triangles, or both of the runner situations. The angle between the first two is larger than his side opposite is longer. All right, and then something cool today. We're looking at a new type of proof. It's called indirect reasoning, indirect proof. And the reason it's called indirect is because you're not starting at the beginning and directly going to the end. You're starting by doing something kind of weird. You're assuming that the conclusion that was reached is actually false. You're going to say, no, I think this is wrong, which seems totally like the opposite of what you would want to do. But you're going to temporarily assume, you're going to use these words always in an indirect proof. You're going to say, temporarily assume that their conclusion is false. Assume that their conclusion is false. Assume they are wrong. Whatever they say at the end, then this is true. You're going to assume they're wrong. And you're going to go with that. And you're going to say, if they're wrong, here's what happens. But obviously, we're still trying to prove a statement that ultimately is true. So by assuming they're wrong, you're going to lead to a contradiction or a logical impossibility. Something's going to go wrong. It won't work out. Assume they're wrong, but it doesn't work out. You're going to find that, oh, assuming they were wrong, I guess it doesn't really work. You know what? I guess you were right all along. I was not correct by assuming you were wrong. I'm sorry. You're right. When I was saying you were wrong, I was being mean. You did the right thing. Because it won't work out. It'll lead to something not true, and then you say, okay, I guess the conclusion must be true. I guess what you said is true because me saying it was wrong didn't work out. Because it led to a contradiction. Okay, so indirect reasoning it does seem really weird. You're going to assume that the statement you're given is wrong. You're going to show that if it was wrong, though, something doesn't work out. It's a contradiction. It's impossible. I guess it was true all along. Let's give this a try. So I'm going to write an indirect proof for this statement. If x plus y does not equal 14 and y equals 5, then x does not equal 9. And actually, this statement, you should be thinking it is correct, because if you know x plus y doesn't equal 14 and y equals 5, if y equals 5, and you subtracted 5 on both sides, you notice x does not equal 9, right? 14 minus 5 is 9. So yeah, we know that they're right. But the way we're going to show that they're right is by starting and assume they're wrong. I'm going to assume this is wrong. Their conclusion. That's how you actually start indirect proof. Assume their conclusion is wrong. So I start out and I use these words, generally always right at the beginning. Temporarily assume that this is wrong. So instead of x does not equal 9, I'm going to temporarily assume that x does equal 9. I'm going to say that their conclusion is wrong. Okay, I'm going to assume x does equal 9. But I'm going to use this and everything else I had, and I'm going to show that there's something that contradicts itself, that goes against what it said. So I'm going to assume that x equals 9. And then, remember how I was given that y equals 5? So I'm going to say then, since y equals 5, right? That was what was right here. I now have x plus y. Remember how that's what we're trying to say here, and we know this is still given. This is still something that has to be true, is that x plus y can't equal 14. But I now have that x plus y equals, well, x was 9 plus, and again, y is 5, which I'm going to move this statement. I'm sorry, I just want more room. Okay, then, since y equals 5, I now have x plus y equals 9 plus 5 equals 9 plus 5 equals 14, right? But that wasn't supposed to happen. X plus y was supposed to not equal 14. But I was also given that x plus y does not equal 14. So I have a contradiction, right? It's going against what it said at the beginning. I have a contradiction, and I know that x does not equal 9. I know that they were right all along, because I was temporarily assuming that x equals 9. I was going against what they said, but it led to a contradiction. It then went against something they said earlier, okay? So I know that x really doesn't equal 9. I guess I was wrong here. I said x does equal 9. It didn't work out with what I was given. I guess they were right. X doesn't equal 9. So it's like this very backwards way of thinking and getting to a proof. It's starting out assuming they're wrong and showing that, well, if they were wrong, it's not going to work out anyway, so they had to be right, since them being wrong can't lead to any logical conclusion. Let's try this in one more case here. I'm going to write an indirect proof of the corollary of the triangle sum theorem. Remember the triangle sum theorem said angles in a triangle add to 180? Triangle sum, right? Sum means adding up. Angles in a triangle add to 180. That's what triangle sum theorem said. But the corollary to triangle sum theorem said the acute angles of a right triangle are complementary. The acute angles of a right triangle are the two angles that are not the right angle. Complementary, remember, means add to 90 degrees. So corollary of triangle sum theorem says that if you're given that you have a right triangle, so you have angle C as a right angle here, then the two acute angles, measure of angle A and measure of angle B, would have to add to 90. I'm going to prove that this is true by showing that it not being true doesn't work out. That's indirect proof. So the thing is, I had to assume that this was false, but instead of angle A plus angle B does not equal 90, right, assuming this is false, and the opposite of equals 90 would be does not equal 90 degrees, but it's actually easier to do two cases here. First, I'm going to assume that measure of angle A plus measure of angle B is greater than 90. Then I'm going to have to do angle A plus angle B is less than 90. So I have to do greater and less than. So temporarily assume that measure of angle A plus measure of angle B is greater than 90. But what would that mean if these two angles add up to more than 90? Since the angles in a triangle add up to 180 by triangle sum theorem, then by triangle sum theorem, what would the measure of angle C have to be? If you knew that A plus B was greater than 90, what's left for angle C to add to 180? Well, wouldn't it have to be less than 90 degrees? Because something greater than 90 plus something less than 90 would equal 90 degrees. And angle C could no longer be 90 degrees, but I was given that angle C is a right angle. And if angle C is less than 90, it's not a right angle. But we were given angle C is a right angle, which is a contradiction. So it can't be less than 90 because it's a right angle. So we have a contradiction. So apparently this cannot be true. Case 1, that measure of angle A plus measure of angle B is greater than 90 does not work. Case 2, we're going to temporarily assume. We're going to say, once again, I think you were wrong. I think A plus B maybe doesn't equal 90. Maybe measure of angle A plus measure of angle B, instead of being greater than 90, maybe it's less than 90 degrees. But once again, if you think about it, if A plus B is less than 90, I know the angles in a triangle add up to 180, right? By triangle sum theorem. I say then, by triangle sum theorem, what do you know about the measure of angle C? If A plus B is less than 90, angle C has to be more than 90 in order to add to 180 by triangle sum theorem. But again, this contradicts the fact that we were given angle C as a right angle. But we were given angle C is a right angle. Well, it can't be greater than 90 because then it's not a right angle. So once again, we have a contradiction. Both cases for us didn't work out, By saying they were wrong, we were led to a contradiction. We were shown to be false. Therefore, after all of this, I know that what they said is true, because showing they were false did not work. They were right all along. Measure of angle A plus measure of angle B does equal 90 degrees. So today, working with hinge theorem and indirect proof.